Hey everyone, thank you for joining us for the Biostatistics Epidemiology Research Design Seminar Series. My name is Lan Kong. I'm Professor of Public Health Science at the Penn State College of Medicine in Hershey. My counterpart at University Park is Mosak Chow, who is Professor at the Statistics Department. You can reach out to us using this email address, ctsi-biostat. The registration information for all the seminars is available now. You can visit on this CTSI website and the research support, then seminars to sign up for the seminars you are interested in. So this seminar is recorded. You have to use the QA box to submit the questions because you are not allowed to speak. All the registrations will receive the slides, recording link, and feedback survey after the seminar. So now let me introduce our seminar speaker today, Alan Kunselman. Alan is the senior instructor of biostatistics and a key faculty member of the CTSI BERD core. After receiving his master's degree in statistics from Penn State in 1994, Alan joined the Penn State College of Medicine as a data analyst. He has become the director of our biostatistics consulting since 2005. During the last 28 years, Alan has successfully collaborated with researchers from a variety of medical fields, leading to over 250 peer-reviewed publications. His expertise is in the design and analysis of clinical trials and observational studies. He has served as the primary biostatistician on many federally funded clinical studies. The topics of his presentation today is the basics of randomization and sample size estimation. So Alan, are you ready? The floor is yours. And I think you are muted.
I'm sorry, can you see my slide, Lan?
Yes, perfect.
Okay. Thank you everybody for joining us, and sorry for the little bit of a hiccup there with getting my computers going. Well, thank you everybody for attending. And this is a talk that's more just give you the basics and background of two topics, randomization and sample size estimation. So you don't need to be scared off of any Greek symbols or math formulas, but I think this will give a good introduction and why these issues are important. I just want to make sure the slide moved, did it?
Yes.
Thank you. So the first thing to talk about is randomization. So a randomized controlled trial is considered the strongest design for evaluating the effects of an intervention. And advantages of the randomization are they avoid selection bias. And what selection bias is, it occurs if your allocation process is predictable. So for example, even if you think you're randomizing somebody, if you're doing a study where all your patients are going to be assigned to treatment A on Monday and treatment B on Tuesday, and then treatment A again on Wednesday. So every other day you're switching to treatment. That isn't really randomization. You'd have selection bias. You would know when those patients are being randomized. And this comes into importance, for example, in an open label trial. So say your trial was half your patients would receive some type of device and the other half would not receive the device. So because it's the device, it's open label, you can't really blind it. And not that you want to do this, but you could say, well, if I was a physician, this patient really isn't going to benefit from what they really would benefit from having this device. So I'll make sure they come in on a Tuesday, so they're assigned this device. So there's biases that can introduce. So randomization helps you avoid that. It also produces comparable groups in terms of both known and unknown prognostic factors. So it helps you minimize accidental bias, which is confounding variables. And randomization also adds validity to your statistical tests. And there are two really main branches of randomization procedures: fixed allocation and adaptive. So fixed allocation is when you assign the interventions to the subjects with a pre-specified probability, typically equal. And the allocation process is not altered during the trial. And there are four typical methods, but there are more than these for fixed allocation: simple randomization, blocked randomization, stratified randomization, or stratified permuted block randomization. And I just want to bring up here, many of you may be doing your future research projects using REDCap to store your data. One nice thing about REDCap is it does have a randomization module built into it, but it only does fixed allocation randomization. So within REDCap, you can create your randomization list and upload it into REDCap so the pharmacy could actually assign the patients for you to keep you blinded. By pharmacy, I mean the investigational pharmacy. And so it can do simple randomization and it can do stratified randomization. So keep that in mind. We get later to adaptive randomization. That is one thing REDCap cannot do. It cannot do adaptive. It can only do fixed. So let's start out with the simplest method, just simple or complete randomization. So this makes each new treatment assignment without regard to those already made. So for example, let's say we have two treatments, A and B. And for each new subject randomized, the probability a subject is assigned to either treatment is 0.5 or 50%. It's like flipping a coin. So the randomization list is just basically a list of A's and B's for 10 subjects. So for example, if you were to flip a coin, heads is treatment A, tails is treatment B. You flip it the first time, you get a head, so that first person gets A. The second coin flip for the second patient, it might come up tails, so it gets B. So like I said, it doesn't think about prior randomizations. Each one is a unique, A or B, 50-50, this person's going to get one of these treatments. So the advantage of this, it's very easy to implement. The big disadvantage is the potential for substantial imbalance in the number of subjects or distribution of prognostic factors between the groups, especially for small studies. As you can see, even as a small example, I hear of these 10 subjects, there are 6 Bs and 4 As. But you can imagine if you only assign 10 subjects, you can flip a coin 10 times and you could get 8 heads and 2 tails. So you can get a really big imbalance in your 2 treatment groups with complete randomization. Now, the more subjects you recruit, that'll minimize and go away. But these imbalances don't cause their stat test to be invalid, but they do reduce the availability. Yeah, I can't talk. Reduce the ability to detect true differences between the groups. So you reduce the power in your study. So what's one simple way to fix this is to do blocked or permuted block randomization. And what this does is it adds a simple constraint that improves the balance in the number of treatments assigned to each group. So this block would contain a pre-specified number and proportion of treatment assignments. And the size of each block must be an exact integer multiple of the number of treatments. So for example, if you're assigning 2 treatments, your block sizes should be 2, 4, 6, 8, 10. If you have 3 treatments, your block sizes would be 3, 6, 9, 12. So they need to be a multiple of the number of treatments you're assigning. And you can use fixed block or variable block size. And the advantage of doing variable, it's a little bit more complex, but it makes the allocation process even harder to predict for anybody involved in the study. And I'll give an example of this in the next slide. But the sequences of these blocks make up your randomization list. And after all assignments have been made, each block in a treatment group is balanced. So let's just look at an example for this block randomization. Again, let's assume we have 2 treatment groups, A and B, and we want to randomize a total of 20 subjects, 10 to treatment A and 10 to treatment B. And we want to use a fixed block size of 4. So when we think about this block size of 4, how many possible permutations can you get with a block size of 4 in 2 treatments? Well, there are 6. It could be AA, BB. The first person can get A, the second person B, A, and then B. And you can see I listed the 6 here for you. And you can label these 1 to 6. So, the first block is AA, BB. The second block is AB, AB. And then what you can use a pseudo-random number generator to select 5 numbers with replacement from those 6 labels. And why am I selecting 5? Because we want a total of 20 subjects and a block size of 4. So 4 blocks times 5 would be 20, give you your 20 subjects. So let's assume this RNG, these 5 blocks we pick the numbers 2, 1, 4, 2, 5. Then our final randomization list will be, it would pick block 2, which would be AB, AB, and then block 1, which is AB, BB. Then pick block 4, which is BBAA. And because we did it with replacement, it picked block 2 again, ABAB, and then block 5. So this would be our treatment. And as you can see, it's perfectly balanced. With all 20 subjects, we have 10 A's and 10 B's. And within each of these little blocks, there's 2 A's and 2 B's. And one advantage of doing a block like this is, say we definitely want to get 20 subjects, but for some reason the study had to end early and you could only do 16. When you have a balance like this, even if we didn't have these last 4, we'd still have balance 8 and 8. Well, what if we only had 15 subjects? Well, it wouldn't be balanced, but it'd be as close as we could get it. We'd have 8 A's and 7 B's. So having these block sizes do help. It balances. You get everybody you want to recruit, it definitely be balanced 100%. But if you end up short, you can have good balance. And so how would a variable block size work? Well, you could do variable. We could have 2 blocks of size 8. So that would be 16 subjects, and 1 block of size 4 to give us our 20. And what does that do? Again, we have 20 subjects, 2 blocks of size 8 and 1 block of size 4. It just makes it harder for somebody to predict, because a block size of 8, 1 permutation could be 4 A's and then 4 B's. So you get these bigger patterns of it's harder to detect what will be happening for the next randomization. So the next twist into this is to do a stratified permuted block randomization. So what stratification does, it balances several clinically important prognostic factors across your treatment groups. And prognostic factors are things that are known to be strongly associated with the outcome of interest. So for example, let's say our primary outcome in a study was forced expiratory volume, or FEV1. And you're looking at 2 treatments, a placebo and a drug that would help you increase your FEV1. Well, a prognostic factor or potential confounder, you could say, could be smoking status. Was a person a smoker or non-smoker? Because that would have a direct effect on their FEV1 values. So every relevant prognostic factor combination can define an individual stratum with blocking in each stratum. And treatments assignments will be balanced within each of these strata, yielding balanced prognostic factors in the treatment group. But there is the possibility of treatment imbalances as the number of strata increases. So you could have a lot of potentially confounding factors you want to balance for. Let's say it was smoking status, age, young versus old, sex, male versus female, diabetic status, yes or no. But the more of these strata you try to balance for, the higher the probability that you're going to have a big imbalance in your treatment assignments. And hopefully I'll explain this a little bit better to follow. But in the following example, say at the end of the study, back to our 20 people, we want to stratify on smoking status. And we had 4 smokers and 16 non-smokers. So we have 2 strata. So our assigned 2 strata could be smokers, we could have A, BBA, and non-smokers, we may have picked these patterns. And where I get into imbalance, let's say we only had, you never know when you start out with the study, smoking status is a problem, but let's say only one smoker came into your study. Well, that one smoker would have been assigned treatment A, and then everybody else would have been in these other blocks. So you wouldn't have 10 A's and 10 B's at the end. You might have an imbalance of A's and B's because you didn't have that many smokers. And it's hard to see with this example, it's only one strata. But again, you have 5 or 6 strata, you may only have 1 or 2 people that were smokers that are young, female, that do not have diabetes, etc. So stratified randomization is a really good thing to do, but I recommend you only use it if you have 1 or 2 stratification factors. The more subjects you can do in a study, the more strata you can involve, but there are better, the adaptive randomization methods I'll talk about in the future are better for when you have multiple strata to worry about. And as I mentioned before, REDCap can do stratified randomization like this. So that's a good thing with REDCap. So I'm not going to go into real detail about adaptive randomization other than to give you a quick overview of it. And what adaptive randomization does is it changes the allocation probabilities as the study progresses. So the big advantages of this are it's flexible, you have better balance, especially for a large number of covariates in smaller studies, and the methods are complex. Disadvantage of the methods are more complex and are typically much more difficult to implement than fixed allocation. Sorry, Sarah, I hope I answered your question. I just saw it now. REDCap can do simple randomization and stratified randomization, not these adaptive randomization methods. And when I talk about more complex, is you'd have to have, it's going to cost money because it's not simple to do. Somebody would have to program these adaptive randomization methods. So you'd have to account for that in your budget. A lot of pharmaceutical companies definitely do adaptive randomization, but they have a lot more money and resources to afford to do a lot of these things. But it's a very good approach to do. So just let you know, there are 4 major types of adaptive randomization. And I'll go through each of these briefly. So restricted randomization is it uses your past treatment assignments to select the probability for a future treatment assignment with the goal to balance the number of subjects across the treatment groups. And you may have heard of a biased coin design. And so what does this mean in practice? It means if you're doing a restricted randomization, let's go back to our 2 treatment groups, A and B. The first person in that study flipping a coin has a 50-50 chance of being in treatment A or B. But that first person is the only person that truly has a 50-50 chance of being in A or B. So let's say we flip the coin and this person gets assigned to treatment A. So what restricted adaptive randomization says is, okay, we know subject 1 received treatment A. Now we need to assign treatment B, the second person. And we'd really like a B to help balance this out. So instead of 50-50, we're going to have a 50.5% chance of subject 2 getting treatment B and a 49.5% chance of subject A. So it's biasing it a little bit toward treatment B. So then you flip that coin for the second person. Let's assume it comes up treatment A again. Now we have 2 A's in a row and no B's. So the process thinks, okay, we really need to get a B to help balance this out. So now we're going to bias this coin more, and it's going to be like a 51% chance to get a B and a 49% chance to get a A. Flip the coin again. If it comes up B, then you have 2 A's and a B, and then the probability slightly balance back. So it's always adjusting these probabilities to help balance it. I'll do an extreme. Say you got not 10 A's in a row. That biased coin to get the next person in might be a 99.5% chance to get a B and a 0.5% chance to get an A to try to balance it out. I hope that was understandable. So the next is just a twist on that. So it's a covariate adaptive randomization. So what this does is uses past treatment assignments and patient covariate values, your prognostic factors, to select the probability of future treatment assignments with the goal to balance both the treatment assignments and these covariates. And you may have heard the term minimization. And I don't know if it's still the case because I really don't do much cancer research, but I know in the 80s and 90s, minimization was the go-to type of randomization used in many, many cancer trials. And this is the method that I mentioned before. If you have a lot of strata that you're trying to balance for, using adaptive randomization with this covariate adaptive method is what you want to use, minimization. So again, what it says is, it takes, so person one, you flip the coin and they get treatment A. But we also know they were a smoker. So when the next person, the next smoker comes in, might be the 10th subject you see, it takes into account, okay, we already have one smoker and they got treatment A. So we're going to balance this coin to B and smoker. So what it does is it's kind of using that same idea, stratified randomization, but it's much more efficient and can handle many, many more covariates than what stratified randomization does. It'll give you a better balance of A's and B's in the end. And then the next method is response adaptive. So what this does, again, uses your past treatment assignments, which is what was the prior person assigned, treatment A or B, and what the actual patient responses to select the probability for future treatment assignments. So you may have heard the term play the winner. So what does this mean? So this is only really good if you know the response to the treatment fast. Like you give a treatment and you know within an hour, did it work or not, or within a day. If you're trying to say, did treatment work a year later, this isn't the thing to do. Because what it's trying to say is, we randomize the first person and say they get treatment A. And we give them that treatment and say the whole study is insect bites. And the treatment is this, we're testing the standard cream versus a new cream for the effectiveness, how fast you're not going to itch anymore. And so the outcome could be, are you itchy in 1 hour, yes or no? And you could look at these creams and say, you do the treatment, an hour later, you look at it and ask the patient, did this cream work for you, yes or no? And that's the assignment. So say treatment, the first person gets assigned treatment A and they say, yes, this treatment worked. Well, then the next person assigned is going to take what they were previously assigned, whether it's A or B, and weight the coin and balance it out. Assignment. So the term play the winner comes into play. Let's assume we had 5 treatments we were looking at. So it keeps assigning the treatments that seem to be working. So eventually, the treatments that aren't working, the chances that a subject later down the line will be assigned that treatment is very small. It might only be like, 50 patients in, it might be a 1% chance that somebody's going to be assigned treatment E because it's been shown it's not really working. So eventually, only the cream of the crop treatments rise to the top and keep getting people assigned. And advantage of this, it saves resources and you don't have to pay for drugs going on that aren't working. And then this last method is covariate adjusted response adaptive randomization. So it's just a combination of the middle two. It's just taking it to the next extreme. Before I move on to the next topic, which is sample size, does anybody have any questions they want to ask me now about the randomization, or it can wait till the end if you want to, but I just want to give you a brief overview of what randomization is, why it's important, and especially what REDCap can and can't do. Because okay, well, if you have questions at the end, just let me know. So next topic I just want to briefly go about is talk about why is the IRB and NIH and other places that you're trying to find funding for, why they worry about sample size and power. Well, there are scientific reasons. You want the study to be big enough to statistically detect a scientifically meaningful effect. But you don't want it so big where the effect has little scientific significance, but it's statistically detectable. So an example I like to use here is, let's assume we're looking at a sample of hypertensive subjects. And we're going to look at treatment A and B. A is a placebo, and treatment B is a new drug that we think is going to lower your systolic blood pressure. So on average, let's assume that all these hypertensive people in the study have an average systolic blood pressure of 160 millimeters of mercury. So what will be a scientifically meaningful effect? Well, I think if we could reduce that by 25 millimeters of mercury, going from 160 to 135, I think a lot of physicians say, yeah, that's a scientifically meaningful effect. So you want to get enough people to show that 25 millimeter mercury drop between the placebo group, which we assume is going to stay at 160, and the treated group that's going to go down to hopefully 135. But what do I mean by too big? Well, if I had 10,000 people, 5,000 people in each group, I could probably do a study and tell you the p-value is going to be less than 0.01. And if you took p-values at face value, say, oh yeah, this drug is effective, we got a significant result, my p-value is less than 0.01, it's really working. But with that many people, I could show you that a 1 millimeter mercury drop going from 160 to 159 would be statistically significant, but that would be totally clinically irrelevant. Nobody cares about dropping your systolic blood pressure by 1 millimeter of mercury. So there's a balancing act there. There's economic reasons. An undersized study wastes resources and money by not having the capacity to produce useful or definitive results. Oversized study uses more resources, money, and necessary. So if you don't want to pay for a lot of researchers' time or coordinators' time recruiting subjects if they're not really needed. And then there's ethical reasons. An undersized study exposes subjects to potentially harmful treatments without advancing knowledge, whereas an oversized study can expose more people than necessary to potentially harmful treatment, or it could deny potentially beneficial treatment. So that last little bullet point is, let's say our new treatment is really effective, and we could have shown that with 300 people. Well, if the study's oversized and we're recruiting 10,000, it might take us 5 more years and delay this really good treatment that we could have known with 300 people. We could have known, 5 years earlier that this was working well. So in short, what sample size estimation is important for in study design, it ensures validity, accuracy, reliability, scientific integrity, and ethical integrity for the study. And grant reviewers and IRBs are looking for sample size and power considerations for your studies, especially if it's a prospective study. So what are some approaches to sample size estimation? I've listed 3 here, but there are more. I'm not going to talk at all about really the Bayesian approach to optimize a utility function or a cost function. That's just one approach. An approach you may see sometimes is a precision of estimation, where you specify the desired width of a confidence interval. So for example, let's say you wanted to know, I really want to get an estimate of what percentage of the patients that I see think our waiting time is too long in the queue, and you survey them. Well, how many people do you need to survey to determine if they think your waiting time is too long? Well, it depends on how much precision. If you asked 10 people and 9 of them said, yes, it's too long, 9 out of 10 is 90%, but the confidence interval for that would be very wide because it's only based on 10 people. Whereas if it was 90 out of 100 people, again, that's 90%. Your confidence interval will be much smaller because you have 100 people. If you have 1,000, it gets smaller. So how much precision do you want to know? Plus or minus 1%, plus or minus 2%, because that can drive your sample size approach. But the most popular and one we're going to spend time talking about today is the power of a test of hypothesis. It's the most common approach used for stat power estimation. And so what are some elements to this? Well, you specify the null hypothesis in either a one-sided or two-sided alternative hypothesis on some parameter you're trying to test, a mean, a proportion, for example. And even though you think, I'll say probably 95% of your project should have a two-sided alternative hypothesis, even if you think it should be one-sided, like drug A is better than drug B, you want to do a two-sided test because the two-sided test also tests not just for benefit, but can also test for harm. There are very rare situations where you really want to do a one-side hypothesis test. So another thing you need to know is the effect size. What's the deviation from the null that's deemed clinically meaningful? Back to my hypertensive subject example, the effect size there I was talking about was a 25 millimeter mercury drop. So that would be my effect size. Variability is the inherent uncertainty. And if you have a continuous variable like systolic blood pressure, there the variability is the standard deviation. What is the standard deviation of my systolic blood pressure? Then you have the significance level, which you a lot of times see as alpha, and that's your type 1 error. And your type 2 error is known as beta. And power is actually the complement of your type 2 error. So power is equal to 1 minus your type 2 error. And then finally, a sample size is how much evidence do I really need to collect? And many of you have probably seen this before, but I'm going over it. What are these types of errors? So in this little 2x2 table, the columns are the true answer, and the rows are your study trying to make a decision about it. So if in truth your null hypothesis is true, and in your study you do not reject the null, then you made the correct decision with 1 minus alpha. And if your alpha is 0.05, then you made the correct decision 95% of the time. If your alternative hypothesis is true, but you failed to reject that, you've made a type 2 error, which is claiming that you found a difference when truly one doesn't exist. I'm sorry, you made type 2 error. I said that wrong. A type 1 error is when the null hypothesis is true, but you claim there is one, you reject the null. So in general, type 1 errors are considered much more serious. And as your type 1 error decreases, your type 2 error will increase and vice versa. Generally, you'll see your type 1 error set to 0.05 before the experiment, but 0.05 isn't a magic number. You can have your type 1 error be 0.01, which can be a more powerful study. And your type 2 error is going to depend on your alternative hypothesis, test stats, and sample size. So I don't know if any of you have seen this analogy before, but to a jury decision. So think about your null hypothesis that there's no association. So put yourself in place of the prosecuting attorney in a case. His null hypothesis is that the person on trial is innocent of the crime. But what the prosecuting attorney is trying to prove, his alternative hypothesis, that he is guilty. So if he wins the case and he claims there's association there, but there wasn't any, basically, if they convict an innocent person, that's making a type 1 error. If they claim there's no association when there actually was one, that is, they acquit a guilty person, that's a type 2 error. And I think most of us agree it's more egregious to send an innocent person to prison than it is to let a guilty person go free. So I hope this helps understand that a little bit. So back to these elements. So we have effect size. The effect size is the size of the deviation from the null that we wish to detect in our sample. And again, as I mentioned previously, like think about the 25 millimeters of mercury is clinically important difference you'd want to detect. And a lot of times it's the most difficult aspect in sample size planning, because you may not know, especially in early stages of research, like bench science especially, you don't know what might be a really important effect. But you want to make an informed guess from prior studies. So you can look at pilot studies, you can look at you can do your own pilot study, you can look at other papers that have done similar research. So there's also something known as a standardized effect size or relative effect size. And what this is it takes the effect size and divides it by the variability. So for example, if our effect size in the blood pressure example is 25, and let's assume the standard deviation is 10, then 25 divided by 10 is 2.5. So that would be our standardized effect size. Usually a good study will have a standardized effect size between 0.1 and 0.5. And kind of what it means is a 0.5 means your alternative hypothesis 0.5 standard deviations away from the null. What's the big advantage of this? It's unit free. So when you take your difference and divide it by the standard deviation, back to our blood pressure example, you cancel out the millimeters of mercury. So there's no units to it. I'm sorry. Got my slides off. So let's talk about variability. So the greater the variability or spread in the outcome variable, the more likely it is the values in the groups will overlap. It makes it more difficult to demonstrate an overall difference between them. Just think that the larger your standard deviation, the more difficult it will be to find a difference. So where do we get this variability estimate for a power calculation? It can be from experience, from similar studies published in the literature, or from doing a pilot study first. Like you do a pilot study on 10 or 20 subjects, get an idea of your variability, and then use that to power a proper larger study. And more complicated study designs will have multiple sources of variation. So example, repeated measures design, you'd have a within subject variability and a between subject variability to estimate. So complicated designs may have multiple sources of variability. So what is actually power in your study? Well, the intuitive definition is just the strength of your study, and power and effect size are directly related. So that is, all other things being equal in the formulas, the larger the effect size, the more power you have. And power and variability are inversely related. So the smaller the variability means the more power you're going to have. Now, power and sample size are directly related. The bigger your sample size, the more power your study will have. And power and significance levels are directly related. So the bigger your type 1 error you're willing to accept, the more power you have. But you don't want to make your type 1 error large, because that's not a good thing to have for your study. So what are some steps when you do sample size estimation? So if you're doing your study and you go to talk to a statistician to help you do this, what are they going to be doing? We need to state the null hypothesis, and is it a one-sided or two-sided alternative? Select your statistical test. Is this a t-test for like comparing the means of two groups? Is it a chi-square test for comparing the proportion between two or more groups? Choose the effect size and the variability. So what is a clinically meaningful difference that you're trying to detect, and how much variability is there in that measurement? Determine what type 1 and type 2 errors you're willing to accept for your study, and then you can calculate the sample size. So for continuous outcomes, usually if you're coming to a statistician like myself and say, here's a study, my continuous outcome is systolic blood pressure. Things that I would be asking you for is like, can you give me an estimate of the means in each group? Back to my example. So the mean in the placebo group may be 160 millimeters of mercury, and the mean in the treated group could be 135 millimeters of mercury. 160 minus 135 is that 25 millimeter of mercury difference, the effect size. And I'd have to ask you for what's the standard deviation? Is it 10 millimeters of mercury? Is it 20? A reminder is the bigger the standard deviation is, the more subjects it'll take to do your study. A categorical outcome. What you really need are the proportions in each group. Is it 0.2 versus 0.4 or 20% versus 40%? Survival outcomes. Their estimates proportion of subjects surviving until time t. So what's the proportion of subjects surviving until 1 year? Or what's the proportion of subjects surviving until 5 years? So those are looking at survival outcomes. And there are many software packages that can do sample size estimates. There's a package called PASS, which stands for Power and Sample Size. There's SAS, Stata, R, SPSS. And actually, for simple things, there's a lot of free packages. Like if you just go into Google and type sample size for sample size for t-test, you'd probably find a free online calculator that could do it, because t-test and chi-square test are very simple power calculations. Repeated measures design, survival, logistic regression, those are more complicated, which take specialized software typically. So what are some other things you need to consider that would affect your sample size and power for the study? So what's the hypothesis goal? At the very beginning of this, I talked about one-sided versus two-sided and things like that. 95 to, I would say 99% of the studies that you see or do will be superiority studies. Treatment A is more effective than treatment B. And a lot of times you want to, in almost all the studies, even though you're trying to show treatment A is better than treatment B, you do a two-sided test, because as I mentioned previously, a two-sided test lets you test for, is it truly better, or maybe it's worse that you don't know. Maybe it's actually harmful, and you can show that this drug is actually much worse than the other. But there's also non-inferiority trials and equivalence trials. So an example of an equivalence trial is you're trying to show that your two groups give you the same result within a margin. It's called an equivalence margin. So for example, if you were making a generic drug, you would have to show that, prove to the FDA that your drug is equivalent to the actual drug on the market, like that GSK or Merck makes. And it can't be better and it can't be worse. It has to be equivalent within certain bounds, plus or minus. And a non-inferiority trial is you're trying to show that your drug, if it's better, if your, or I shouldn't say drug, if your intervention or treatment is better than, if treatment A is better than treatment B, or that's great. But if it's a little bit worse, that's okay, as long as it's not too much worse. That's non-inferiority. There's special sample size and power calculations for non-inferiority equivalence trials. So other things that go into sample size and power are your designs. Is it a one sample test? Are we just testing the means or the proportions? Is it two samples? Is it 3 or 4 samples? Are the data correlated, meaning like paired data? Do we have a paired t-test we need to think about? More than 2 samples would be like an analysis of variance type study. Longitudinal studies would have repeated measurements. Are we assessing people's data at 2 points in times pre and post, or maybe 5 points in times, baseline 1 month, 2 month, 3 months, 4 and 5. You can have crossover studies. A crossover study is where a subject may start out on treatment A, and after a period of time, they switch over and get treatment B. So actually each subject would get both treatments, A and B. Or you could have more complex, you have 3 treatments. A subject could get treatments A, B, and C at different times. There's design effects like clustered sampling. Is it a dose finding study? So as your study design really goes into how you use sample size and power. And these are things I'm only bringing up for you to consider when you talk to the statistician or consultant about, hey, when you show up, I need a sample size for my study. These are the things that stat person's going to need to know. Well, how many samples and how's the study designed so I can give you the proper calculation. So other issues to consider. I try to get everybody that comes to me to have one primary outcome to power their study on. But you could have multiple outcomes. And why I push one outcome is usually people don't have endless resources. So let's take a simple example. Let's say we had 2 primary outcomes we wanted to look at. Well, now instead of having, for example, your alpha 0.05 that say, is this different? With 2 outcomes, you might need to have an overall 0.05 effect. You can think like a Bonferroni correction type thing. We'd have to have 0.025 per test. So each test would have to have a p-value less than 0.025. That's fine. The problem is it takes more subjects to show that. So every multiple outcome you're going to do, it's going to increase your sample size. And the more outcomes you have, usually, even with 2 outcomes, usually the sample size becomes untenable for most research projects, unless it's a huge multi-center trial. You could have unequal sample size. Not every study has to be, half your people get treatment A and half people get treatment B. You could have, I want a 2-to-1 ratio. 2 people get the new treatment versus 1 that gets the standard therapy. It could be 3-to-1. So you don't have to have equal sample sizes. But you need to tell the statistician that plan, because by default, almost all software package will just give you the equal number per group. So you need to make sure you have that figured out. Dropout. So sample size and power calculations, the number you get back are, these are the number of people the stat test needs, like a t-test or a chi-square test, to have enough power to show for this outcome. So it needs the data for that outcome. The systolic blood pressure example, if we needed 50 people per group, what it expects at the end of this study, you're going to have 50 systolic blood pressure values from group A and 50 from group B. If it's a longitudinal study and people were dropping out, and you only have 40 in group A and 30 in group B at the end of the study, even though you recruited 100 people, your test will be underpowered. So you need to figure out, what is my dropout rate do I expect? Is it 10%, 20%? And inflate your sample size to account for dropouts, because the calculators from SAS or Stata or any of those packages is telling you this is the end that you need complete data on. Other issues to consider be like non-compliance. Subjects aren't following the protocol. Is there provisions in there that we would kick them out because they're not compliant? And if so, that gets into dropouts and things. You have non-response. If you're doing a survey, how many people, you send out 1,000 surveys and 800 people don't respond. How are you going to handle this non-response? If you're going to do an interim analysis, again, this is back to, it's called alpha spending functions and things like that, where if you're going to do one interim analysis, like halfway through your data collection, you're going to analyze the data. And then at the end of the study, you're going to analyze the data. You have to take into account how many times you're going to peek at your data and adjust your type 1 error accordingly. Again, this requires more subjects. If you're looking at your data 3 times, then there are better methods. What I'm going to say, a Bonfermi correction, you're like, oh, 0.0167 per test. But there are things like O'Brien Fleming's method. There are special methods to handle looking at your data, your interim analyses. Multiple comparisons testing. So if we have 3 treatment groups and you want to compare treatment A to B, A to C, and B to C at the end, that's 3 tests. So again, you have multiple testing. You don't want to have, you want to have a global 0.05. So you have to take into consideration multiple peaks at your data. It's kind of like the same thing as interim analyses. You have to account for your alpha accordingly. Are you going to do adjustments for a covariates? How many subjects do I actually have available? And I'm going to have a slide about that in a minute. Do you have sufficient power for an important secondary outcome? Again, you can have multiple outcomes, but you have to plan for that if you have like 2 primary outcomes. And screening for eligibility. So say you have an invasive test that needs to determine eligibility. So the sample size and power calculation, as I mentioned, is only telling you the number of subjects you need at the end of the study with that endpoint. But let's say to even get into the study, part of your inclusion-exclusion criteria is that you have to have a HbA1c level greater than 10%. So you might have to test, 500 people to get 100 people that have their HbA1c level over 10%. So again, the power calculation is only taking into consideration at the end of the study, here's what I need, not how many I need to screen to get into the study. That's something you have to think about, how many you might have to screen to get in. So as I mentioned, dropouts are not directly incorporated in sample size estimation. So you need to do it during your design stage and increase the size of the enrolled sample size to account for these dropouts. So for example, if you think the dropout is going to be 20%, you increase it by a factor of 1.25. So think about the number of available subjects. So here's an example. Say a clinic sees approximately 20 patients per year with a given condition of interest, of whom only 10% they may refuse to participate in your study. So over a 2-year period, the number of available subjects for the study will be approximately 36. And you only have 2 years to do your study. So although most studies need to balance feasibility with study and power, the sample size should not be determined by a number of subjects available. What I'm getting at there is, if you come to me to do a sample size and power calculation for this, whatever this study would be, and I said, you need 100 people, 50 people per group. And you say, well, I can only collect 36. So can you give me a sample size power for that? The answer is yes. It's just mathematics. I can give you a power, tell you what the power would be with 36 people. But to have a study with 80% power, 90% power, the effect size may be so large that it's totally unreasonable. Systolic blood pressure, it might be, oh yeah, for 36 people, I can give you an 80% powered study with alpha equal 0.05 if you can drop your systolic blood pressure by 110 millimeters of mercury. Well, going from 160 minus 110 down to 50, you're not doing your patients any help. So that doesn't help. It should be, you may have to think of another outcome to do, or consider a multi-center trial to do the study. What you don't want to do is just start your study and get your 36, and again, it'd be an underpowered study. It's not going to get you anywhere. So the assumptions that are made for sample size calculation, when don't they hold exactly? So when can your power be smaller than what you think? Well, wrong initial assumptions about the effect size and variability. So poorly chosen standard deviation is one example. So when you do your sample size and power calculation, back to my systolic blood pressure, if I did it with standard deviation of 10 millimeters of mercury, but at the end of the study, it was actually 40 millimeters of mercury variability because these hypertensive people were all over the place, my study would actually be underpowered because it was a poorly chosen standard deviation. You could have the proportion of subjects who improve on placebo therapy may be underestimated. You may have heard of the placebo effect. So even though you might have a placebo versus a treatment, you might say, well, over time, people that get placebo, yeah, their blood pressure is going to drop, but only from 160. It's only going to go down by 1 millimeter of mercury. Yeah, it may have gone down just by a placebo effect of 5 or 10. So you could underestimate that. The properties of collected data don't match the original model. So a quick example of this is if you do a sample size and power calculation for a t-test, that assumes your data is normally distributed. But if your data is actually very skewed, that the test isn't really as accurate as it could have been. I mean, your sample size and power calculation should have been based on the Wilcoxon rank sum test, for example. So you got to think about what the distribution, what the assumptions of the analysis would be. Like I mentioned before, dropouts, they're usually prevalent in longitudinal studies, and you have non-response can affect power as well. And high-powered studies are not immune to all sources of potential bias. So high power does not really protect the study against bad randomization, a lack of blinding, bias sampling, non-response bias, recall bias. So it's great to have a high-powered study, and that's what you want. But again, it doesn't solve, having a high-powered study doesn't solve all problems. And if I didn't mention it before, I think that things are changing, but if you're trying to put in a study to NIH, the lowest power they typically would accept is 80% power for a study. Although I've heard that they're trying to move more toward 90% power being the minimal they'll accept for a study. So how do you report your sample size estimation in your protocol? We'll have a clear statement of your primary objective of the study. What's your significance level, your type 1 error? What's your power? Type of summary or test statistic you'll use for analysis. Is it going to be a t-test or a chi-square test or logistic regression, whatever it is? Whether the test is one-sided or two-sided. And what's the smallest difference to detect in a clear statement? Is it smallest clinically important difference, or a difference that the investigators think is worth detecting, or a difference the investigators think is likely to be detected? And those last two are more like bench science. You really don't know the effect yet. So you want to have clear statements about the assumptions made, how prior estimates of variance and the effect using the sample size estimation. What are the distribution of the outcomes? Planned duration of the study. So how long is the study going to take? Clear statements about the sample size calculation. Was it adjusted for dropout, loss to follow-up, expected response rates, and other things like bias. Any other information that formed the basis for the sample size calculation. So when I write up a sample size calculation, I always put in as much as I can. For example, even I have a sentence, if the effect size and say standard deviation was kind of taken from a similar study published in the literature, I will reference that paper. That way it gives a reader an idea of, I wasn't making these numbers. I didn't just pick the standard deviation out of my head, out of the air. I actually obtained a standard deviation for a study it's not like mine, but it's similar from the paper by X and O authors. So it's clear how it was calculated. And I'm just a couple more minutes and I'll wrap up here. So I just want to give you some examples of write-ups that I've seen are similar to this, or these are really bad examples of a sample size write-up in your protocol. If you were to state the sample size of 60 diabetic subjects has been chosen to provide adequate numbers of subjects for evaluating the treatments. This is basically saying I can recruit 60 subjects and do my study. This tells me nothing about the power of the study, the effect size you're trying to detect, or anything, your type 1 or type 2 error. It doesn't really tell me much. The next example, a sample size of 50 subjects, 25 per group, yielded 80% power to compare a placebo group to an active treatment group. Well, this is better. It tells me, well, I got 25 per group, has 80% power, and it tells me what groups I'm actually comparing, placebo or active. But it doesn't say what I'm trying to detect, like what's my effect size? What's the outcome? Is it systolic blood pressure? Is it HbA1c levels? What is the outcome you're looking for? The next example, a previous study in this area recruited 75 subjects and found a highly significant result. Therefore, a similar sample size should be sufficient for our study. So this paper got 75 people, found a p-value, so we're going to use the same number. This isn't sufficient. You need to tell the person what the power, even though this might be close, you still need to know what the power, the effect size, what variability went into this. What they should have done is taken this paper and pulled the standard deviation out of it to use that into their power calculation, and maybe their effect size, or maybe not. Another example, so a formal power analysis was not done because there's no prior information on which to base the sample size estimate. Well, this is where you take your best clinical guess or do a pilot study first to get an idea of what an estimate is, instead of just saying, I don't have any idea, so we're going to do 20 subjects. You could do a sample size calculation, or at least do a pilot study. So what are some examples of good write-ups? So with 16 subjects per group and assumed within group standard deviation of 25 millimeters, study will have 90% power for a two-sided 0.05 significance level, two sample t-test to detect the difference. I can go on and on, you can read this yourself, but this tells us the power of the study is 90%. The standard deviation used was 25 millimeters. The type 1 error is 0.05. It's telling me it's a two-sided test. It tells me the stat test it's using, a two-sample t-test. It tells me the effect size is 30 millimeters of mercury on the visual analog scale. And it accounts for dropout. So it says they anticipate 15% dropout. So they're going to recruit a total of 19 subjects per treatment group. Another good example is this one. With a sample size of 140 subjects, 70 per group, there's greater than 85% power to detect the difference between the proportion of VTA inducible subjects and placebo and active treatment groups, when the proportion is 0.9 for placebo and 0.7 for active treatment, using a chi-square test, two-sided significance level of 0.05. So again, it tells us the total number of subjects, 140, 70 per group. The power is 85%. What's the proportion in the placebo and the active groups we're looking at? It's a portion of 0.9 and 0.7. Tell me the test they're using, a chi-square test, it's two-sided, my alpha is 0.05. And I think this is the last. I'll let you read this on your own because I'll make my times basically up. But here's another good write-up. This is taken from a JAMA article. Again, it tells you what the power is. It's a two-sided test, alpha is 0.05. It tells the effect size they're trying to get, a hazard ratio of 0.44. That's the effect size they're looking for in this example. So basically, in summary, you want to carefully consider and state your hypothesis to be tested a priori. You don't want to do your power calculation after the study is done. This should be way a priori before collecting any data. Select an appropriate stat test. Is it a two-sample t-test, a chi-square test? Choose a clinically meaningful effect size. Provide an estimate of the variability. Again, previous studies, literature, pilot studies. Select your type 1 and type 2 area you're willing to accept. Calculate a sample size. Adjust the sample size if necessary for dropouts or other reasons. And consult and collaborate with the statistician. And here's a couple of references. And I thank you for your time. See if I can answer some of the questions that came in here.
Thank you, Alan. This is a great talk. Yeah, we do have a couple of questions in the Q&A box. I think the first one is about whether R package, is there any R package that can do adaptive randomization?
I do not know one off the top of my head, honestly, but that doesn't mean it doesn't exist. There's so many R packages out there. I would have to look into that. So I do not know the answer to that. My thought is no, there isn't, because it's usually study dependent, but I could do some searching and get back to you on that. So another question is, what if you determine the analysis you want to use your primary outcomes to inform your power and sample size, but then you have a different analysis for your secondary exploratory outcomes? Do you just talk about that in reports and manuscripts? Yes. So the whole primary outcome, absolutely. Your primary outcome could be one stat test, and all your secondary outcomes could be different. For example, your primary outcome may be a t-test, but all your secondaries might be proportions like chi-square test. That's why the secondary outcomes are more exploratory or hypothesis generating. They're not confirmatory. Your primary power analysis is your confirmatory, and everything else is interesting to report, but it's not confirmed. So it's like, future study may need to look at this specifically. Hope I answered that question. Any other questions anybody has?
No more? All right. So thank you, everybody, for joining us today. Thank you, Alan, for the wonderful talk, always. So our next seminar will be on October 11th. The topic is systematic reviews and meta-analysis. All right. Thank you, everybody. So hope you have a great evening.